Alright. I don't know how to do this chat thing at the same time, but I'll check every once in a while. I was gonna do some preparation for a class, solve some problems. People want to solve with me, that'd be good. The problem is something like this. You have function g, and g equals the size of the set of all the integers x between n and 1, such that the GCD of x and n is prime. Okay. And then you want to show that the sum of g of d is d divides n plus phi of n is always greater than or equal to n. Okay. So try this for small cases. Try this for n prime, for example. If n was prime, it'd be phi of p g of 1 plus g of p. G of 1 is 0. G of p is 1. Pi minus p is p minus 1. So this gives you equality. Okay, what if n was a product of two primes? So pq. Phi of n would be p minus 1, q minus 1. G sums be g of, I'm not going to write g of 1 anymore, g of p plus g of q plus g of pq. Okay, so this won't count anymore. What does this give you? So this is 1 plus 1 plus, so this has at least 2, p and q. Yeah, it's oh wait, oops. So this has a lot more than 2, possibly. All the multiples of p less than q, yeah? You get the chat box separate. Oh. I guess it is a bit more interesting solving this problem like this than normally. But if I do this kind of stuff more regularly, I think maybe more people will show up. Definitely haven't told anyone about it or promoted it. That's my style. Okay, so there's a lot more than 2 here. Could be, so there's p, 2p, all the way up to qp Except QP doesn't work. It's Q minus 1P. Okay, so this Q minus 1P and this Q 2Q P minus 1Q. So it's really Q minus 1 plus P minus 1. And if you plus the 1s, you get P plus Q plus PQ minus P minus Q plus 1. Yeah, so it really is bigger. So if you had an n for which it's true, and you added a prime, you get d divides n, so it's like a new prime, let's say. That wasn't part of n before. And then np. Phi behaves well like this, so it's multiplicative. It's just times 5p, which is p minus 1. And here, the d either contains a p or it doesn't. This is a sum, d divides n. Yeah, so it should be something like this. G of d plus, and the same divisor could have a p on it. It seems to be something like that. Is G multiplicative? Doesn't seem like it. G of P is just 1, and G of Q is 1, but then when you times it, it's like QP plus Q. It's 1 minus 2. Okay, so you have the old sum. Plus 5n, that'll be greater than equal to n. Minus 5n, then you get So we're going to show this is bigger than p minus 1 times n. Hmm. Guess someone momentarily joined and left. I wonder how to make the chat make a sound or something. Oh, that's interesting. My thing must be very lagged. Maybe I can put it side by side. Let's see. Maybe I do this. I think the stream can only see that much of the whiteboard anyway. I can keep the chat and I won't look back. So what happens to g of dp? How do you relate g of dp to g of d? Stuff like g of d versus g of dp. Still says no one's here, but alright, so that's just what I was writing on. Oh no, what? My whiteboard may be closed. Okay. So it must count all the things in g of d, but unless they have a p in them. Now what else does it count? So actually it also counts the like if there was a q, prime q that divides d, it would also count um, the extra multiples of q. So like for example p minus 1. This is not such a simple way to go about it. So if you have g of like q, it's equal to 1. G of qp, it's equal to p plus q minus 2. Okay, so you definitely get p to p all the way up to dp, but the problem is all the divisors, all these multiples can't divide d. Actually, it's all these multiples have to be co-prime to d, isn't it? Okay, maybe use phi to express that. So it's like 5d. So the 5d things that come from p. Okay, and then somehow got to remove. I need to minus something. The q minus 1 here is the 5q. Where does the p minus 1 come from? That's all the extra multiples of q. But now you have to remove the this is a 5p. Mm-hmm. And then the rest is the ones of GCD are primed as not P, so it's still all the prime values of Q. But you could get like, now you could get like 2Q, 3Q all the way up to P minus 1Q. Get more. So any prime that you had before, you can only go up to D on Q. Easier just to find a formula for a G in terms of phi. You got all the Q's, it's the same, but just in case if PQ was lower, that wouldn't work. Kind of like phi of dp on q. As q runs through all the primes, divide d. No, kind of just branching away from the question here. G of PQR. It's all the multiples of P up to QRP. Because they can't contain a Q or an R, so it's actually just phi of QR plus phi of PQ plus phi of PR. It's quite a nice formula. If you had like G P to the K, Q to the L, let's say. It's still only P or Q, isn't it? So it's phi of P to the K, Q to the L. That's fine. And then how would this change if g to the pk plus l and then just times it by an r? No, it's still, it'd be 5p to the k, q to the l plus phi of plus phi of p to the k, q to the l minus 1 r. And then this is just 5p to the k, q to the l plus g of the previous thing. Maybe that's true. Okay. I think it's something that I can probably prove later. Let's assume it for now. Let's see what we get. If we assume that, then it's phi of d plus phi of p times the 5p times g of d. So we have sum d divides n 5d plus 5p g of d. And this is equal to n plus phi of p sum d divides n g of d. Let's see what else we got here. Okay, well that's promising because this thing here, no, this thing here is just p minus 1. This thing here, well that thing here plus 5n is bigger than or equal to n. So maybe we could think of it as this thing here plus 5n. So minus p minus 1 5n. Then we have the n from here. we need this to be bigger than n times, we need this to plus 5n p minus 2. And we need this to be bigger than or equal to n times p minus 1. This is n plus, n minus 5n. N minus 5n bigger than n times p minus 1. Something is slightly wrong because this doesn't have any p's in it. Let's review these steps. Now that we know what kind of formulas to expect. So we have sum d divides n g of d. This is np now. Plus phi of np. This becomes, if you do the divisors that don't have p and the divisors that do have p, it should just be like this. And it's 5n. Oh wait, maybe I did, that's what I did wrong. So 5n times p minus 1. Oh, I think I had p minus 1 before. Okay, and then sum of d divides n g of d. This thing separates, and then this thing, g of dp, is just g of d plus g of it's plus phi of d. Plus g of d phi of p. I think that's what it is. plus 5n p minus 1. So if we add, so if we take this just to be n plus the sum of d divided ng of d, this term here is this one here, and there's 5p of them there. So we need 1 plus, so this is just p. We need p of those, p phi n's to make that work. We have p minus 1 phi n's. Yeah, so if you plus phi n here, okay, so we have the phi n from before. We plus, this we do g and plus phi n, and we put here p. So we almost have enough. We only had p minus 1 phi n's, so that's a minus of phi n here. So which is kind of inconvenient. If it just worked out without that, it would be much better. So let's see. Maybe it doesn't make a difference. But this thing is greater than or equal to n, right? So this whole thing is greater than or equal to np plus n minus 5n. Yeah, so actually this is true because all we have to do is show it's greater than or equal to np. And this means n minus 5n needs to be greater than or equal to 0, which it is. Phi is always less than n. So it's true when you add a prime. What happens? Let's see if anyone else is still here. Yes. It's hard to ask questions, but maybe just a reminder that you can rewind even though it's a live stream. Okay. Okay, that pretty much solves the problem. Let's see what happens if you add a prime that's already there. G of p to the k. equals so basically it's equal to, let's see, phi of p times g of the original offset. Is it the same formula? So if you have g of like p to the q to the m r to the n, it was phi of p to the l minus 1 and p to the l q to the m r to the n minus 1. And if you increase one of the powers by 1, let's say l plus 1, then what would you get? You'd get everything with the power greater than 1. So these things here are phi of q to the m r to the n times, oh no, it's not. This equals phi of p to the l plus phi of phi of p to the l plus 1 q to the m r n minus 1. And so the formulas for these phi's are all pretty simple. So there's a let's see, I don't know how many q's there are. There's always going to be a p minus 1, q minus 1, r minus 1. And then it seems to be p to the l minus 2, q to the m minus 1, r to the n minus 1, plus p to the l minus 1, q to the minus 2, r to the n minus 1, p to the l minus 1, q to the m minus 1, r to the n minus 2. Okay. And here it's the same thing, I think, but with smaller p. P minus 1, q minus 1, r minus 1. And I'll just write the powers now. I'm not going to write the PQs. So it's L minus 1, M minus 1, N minus 1, N minus 1, N minus 2, N minus 2, N minus 1, L and L. So you can see all the terms are the same. It's just the P to the L. So basically this thing is equal to it's equal to P times G. Yep. So if it's already there, you times it by P. If it's not there, you times it by, well, you add it something. What did we do before if we had it? Yeah, so here this is a G of dp. It becomes, you add phi and then you times it by 5p, which is different than what we just did for. Yeah, so we're adding to the same prime. The prime just comes out. Well, that's pretty nice, isn't it? Okay, does this work? Let's see. So it's the same expression, but the p might not be different. The p could just be part of n as well. Just increase the power. This line is still true. It's still true, I think. And then here, G of dp now is different. Oh, if p is in D. So maybe we could separate the primes that have p's in it, those that don't. The primes that do have p's in it, the p just comes out. Things that don't have p's in it, that's something else. How do I do that? Let's assume. Oh, I know. Let's assume we have np squared. How about that? That's maybe a nice way to start. N doesn't have any p's. So we know it's true for np squared So this is g of d plus g of dp, g of dp squared. Yeah, this might be the nice way to do it. That's 5n 5p squared. Okay. So now how g of dp works. I get sum of d minus n, g of d is phi of d plus phi of p, g of d plus I think this is just g of dp times p. Which, yeah, I can just do it again. Do it again. Replace this by g of d phi of p plus g of phi of d. And this is all multiplied by p. And so you get okay, so the phi of d's turn into n's. See what the sum d and g of d. How many of these are there? There's one from the first term. There's a 5p. There's another 5p times p. And that's it. And then you have this np plus n. You also have this 5n 5p squared. P plus p squared. Is that p squared? This is p minus 1 times p, and this is just p. So I need p squared 5n's to make that work. Here I have p times p minus 1. So I need a, and this is p plus p minus 1 times p squared. So I need p more of 5n's. So I get p squared. This is greater than or equal to p squared n p squared n plus np plus 1 minus 5n times p. So it's supposed to be greater than p squared n. I'm kind of wondering where this p plus 1 comes from. It's n for the 5t. Yeah, so it just has to be greater than p squared n, right? So this just needs to be, like, it's p squared n plus, and it's p outside of n minus 5n. And we got an extra n for some reason. Okay, I mean, it's still bigger than that. Okay, I'm pretty convinced. I'm convinced I can do this. Maybe I'll leave the rest as an exercise for the students. This is, or even as an exercise for myself as I present it or something. Low energy live streams. Anyone here? For some reason it's more tiring doing this like this, but yeah, there you have it. Should be actually, this is kind of algebra, it's not really number theory. But oh. Alright, I think that'll do for now.